All right, everyone, before we get to exam caliber examples of looking at how we track resonance and examples of that, let's talk about how we identify delocalizable electrons. Now, delocalizable electrons are electrons that are resonating, right? So the first instance of delocalizability is when we have a conjugated system. Conjugated systems have alternating double and single bonds. For example, we have here an alkene pi bond, then a sigma bond, and then another double bond. So double bond, single bond, double bond, that is conjugation. And when you have a conjugated system, we can actually resonate across that conjugated system. And as a result of that flow there, I'd make a pi bond here and delocalize a lone pair to that carbon. And then let's track that the carbon on the very end gave up electrons. So that would be positive. So we can resonate across conjugated systems, and each of those pi bonds would constitute a delocalizable pair. There are two delocalizable pairs there. If we look at a benzene ring, all those pi bonds are conjugated in a cyclic fashion. With benzene, we can resonate around the ring like that, and that would simply relocate the location of the pi bonds. So there are three delocalizable pairs in benzene. We count each of the pi bonds as a delocalizable pair. Here's just another example of a conjugated system. You could have a carbon-carbon pi bond conjugated to a carbon-oxygen pi bond. Here, we would probably resonate towards the oxygen because the oxygen is the more electronegative atom. We would make a pi bond there, and then we break the carbon-oxygen pi bond, leaving a lone pair on the oxygen. And then because this carbon atom gave up a share of electron density, it would become positive. Again, we have two delocalizable pairs, counting one pair for each of those pi bonds. All right, conjugated systems. Then we have heteroatoms bonded to pi systems. In the earlier video, we talked about lone pair atoms adjacent to pi systems. Let's treat heteroatoms as lone pair atoms, like oxygen or nitrogen. When you have a lone pair atom adjacent to a pi system, whether that's a C double bond O or a benzene ring or an alkene pi bond, the lone pair atom can make a pi bond, and then we break the adjacent pi bond. So the nitrogen puts its lone pair in a p orbital to engage in resonance. And then I would count the pi bond that would resonate as a result of that flow, also a delocalizable pair. Notice that the oxygen atom here is also a lone pair atom adjacent to the pi system, but only one of those lone pairs can be put in a p orbital. Both cannot be in p orbitals at the same time. One is in a p orbital, the other would be in a hybridized sp2 orbital. So that oxygen could resonate and break the C double bond O. In total, there's three delocalizable pairs, one for the nitrogen lone pair, one lone pair on that oxygen adjacent to the pi system, and then I'd count another pair for the pi bond that would resonate as a result of that movement. But notice that we're not counting the lone pairs on the oxygen as being delocalizable there. They're actually existing in hybridized orbitals. If I looked at this middle example, there's a total of 4 delocalizable pairs. The nitrogen is adjacent to the pi system, so it could resonate in. And those pi bonds are all conjugated with one another, so I can count 1, 2, 3, 4 delocalizable pairs. In this structure here, you'll notice this nitrogen atom is adjacent to that pi system, so it could resonate in and we can move that pi bond. That's one pair. The pi bond that would resonate is the second. You'll notice that these pi bonds there are conjugated, so we could inherently count those as delocalizable. And then this nitrogen atom is adjacent to this pi system. It could resonate into that pi system like so. I'd count one delocalizable pair on that nitrogen and another for the pi bond that would resonate as a result of that movement. Notice I'm not counting this lone pair here as being delocalizable because the nitrogen is already pi bonded. Its p orbital is already preoccupied in that forming that pi bond. So the lone pair cannot be in a p orbital. When we think about lone pairs that can resonate, we're usually referring to a lone pair atom that is visually singly bonded and adjacent to a pi system. That nitrogen being doubly bonded in a ring, its lone pair cannot be in a p orbital and resonate. There's a total of 5 delocalizable pairs. Now, later on in a video, I'm going to go through a larger structural example where we count total delocalizable electrons. But we could say delocalizable electrons, in summary here, would be conjugated pi systems where we count a pair for each pi bond that's part of the conjugated system. And then we can count a pair for lone pair atoms adjacent to the pi system, as well as a pair of delocalizable electrons for the pi bond that would resonate as a result of that movement. Now, we talked about this earlier, but Subtle instances of resonance would be having lone pair atoms connected to atoms with empty p orbitals like boron, aluminum, and the carbocation. What we see here are just more examples of that. Nitrogen can resonate into the empty p orbital of the carbocation, filling that, taking on the positive charge. Similarly, if I had an oxygen directly bonded to the carbocation, the oxygen could resonate a lone pair into the empty p orbital and make a pi bond to the carbon. And we have boron, aluminum, and the carbocation. So if I have an oxygen directly bonded to boron, oxygen could sp2 hybridize, putting one of its lone pairs in a p orbital and form a pi bond to the boron. And then if I had, say, AlCl3, the chlorine could be sp2 hybridized, putting a lone pair in a p orbital and resonate with the aluminum, filling the aluminum's empty p orbital and making a pi bond to the aluminum. All right. So we will later on talk about more examples of delocalizing electrons and specifically counting the total number, but this would be an overview as kind of a preface to that.